Saucier, this is a video lesson on complete transformation of sinusoidal functions. Up until this point, I've left out one common transformation, horizontal dilation. If we compress or stretch the horizontal axis, it affects the period of cosine and sine. And because the period of these cyclical functions is so important, we studied it first before attempting a horizontal dilation which would change the period of a function. We can isolate and focus on horizontal dilation in the transformation equation. If we multiply the horizontal variable theta by the parameter b, then b is going to compress or stretch the horizontal distances and therefore affect the period. To get a concrete idea of this, let's sketch a graph of sine, which starts at its midline and completes a period after 2 pi. If I described a transformation horizontal compression factor 2, then what I'd be describing is taking horizontal distances and halving them. The entire wave would be compressed. Horizontal distances would shrink by exactly half. So this maximum would transform to be halfway to the vertical axis. The period of 2 pi would compress to be a period of pi. The point of the midline will get halfway closer. Sketching the entire compressed wave would look like this. After a transformation, I can see that the period has been affected. The period of the transformed wave is equal to pi. And we can use the common letter P to represent the period. The function for this transformation is going to be a modification of sine. And we're going to horizontally compress it counterintuitively by a factor of 2 by multiplying by 2. Multiplying theta by 2 will have horizontal distances. So, in general, if we've used the parameter b, then the value that we used for this specific function means that the b value is 2. Horizontal compression factor 2. But notice that the period of the transformed function is not the same as the value b that's used in the equation. There's a relationship between b and p, a general relationship, but they're not the same. B is called the frequency. And because we're working with functions that are functions of angle measures, then sometimes we call this the angular frequency. What is the relationship between the frequency or b value that's used in the equation and the very important conceptual understanding of the period? Well, analyzing this situation, we had a period of 2 pi, the period of parent sine. And how did we modify 2 pi to get the new period of pi, the period of the transformed function? Mathematically, we divided by 2, which is the angular frequency. In general, when you transform a function and do a horizontal dilation, then the relationship between the period and the angular frequency is that the period is equal to 2 pi divided by the angular frequency. If you know one of these values, you can get the other. If you have a wave that's graphed and you can observe the period, then you can find the value of b so that you can write the equation. With the inclusion of horizontal dilations, we now have a complete general transformation equation. Y is equal to A times the sine or cosine of B times X minus H plus K. The double parentheses here is really important. If you don't include it, it's going to change what effect these numbers have. These parameters, A is the amplitude, B is the frequency, H is the horizontal shift, and K is the vertical shift. With this complete understanding, we can do something quite sophisticated. For example, we could graph an equation like y is equal to 3 times the cosine of 1/2 times x minus pi, then plus 1. Because the parameters describe transformations on the parent function, in this case cosine. I can, without technology, graph an equation like this. I'm going to first graph cosine, parent cosine, because my graph is going to be a transformation of parent cosine. In this equation, I can observe that the A value, what's multiplying cosine, is the amplitude. We have an amplitude of 3. That means that the wave is going to go up, come back down to the midline, and go down, come back to the midline, and those distances up and down are going to be a measure of 3. I can find the period. In general, I know that the period is equal to 2 pi over the angular frequency. The angular frequency is what's multiplying my horizontal variable. I can see it in the equation that it's 1/2. So the period is equal to 2 pi divided by 1/2. Dividing by 1/2 is the same thing as multiplying by 2, so my period is 4 pi. Again, that describes the wave. If I know that I have a wave that has a period of 2 pi and I expand it to 4 pi, my wave is going to stretch out horizontally. I have a horizontal and a vertical shift. My horizontal shift is the number that I am adding or subtracting to the horizontal variable. In this case, I'm going to change my use of the horizontal variable x to be theta, because my parent function sine and cosine are functions whose input is angles. I have a horizontal shift. If we subtract, then I'm going to go right by pi. I have a vertical shift I can observe. If it was on the other side of the equation with y, it would be y minus 1, and I know that I'm going to go up. These are like descriptions of my wave. Here's how then I sketch the graph. I'm going to first perform on this maximum point here the dilations. The amplitude is going to increase to be an amplitude of 3. So I'm taking the maximum of the parent cosine function at this point, and I'm imagining where it's going to go if it reflects a change of having an amplitude of 3. So the point goes there. The horizontal dilation is not going to affect a point that has no horizontal magnitude. But then I must go right by pi and up 1. The location of this point has been transformed to become this location. If this is the location of the maximum of my cosine function, and I know that the period is 4 pi, then I will find another maximum 4 pi over. So if I'm at pi, I can go to 2 pi, 3 pi, 4 pi, and 5 pi. The space between these 2 points, which are now maximums, is the period of 4 pi. If I know I have an amplitude of 3, then 3 below this point is going to be my midline, and in between these 2 maximums, 3 below the midline will be the function's minimum. I'm reasoning by understanding the concepts associated with these terms and values. So if my midline is at 1, then I must have also expected moving the entire wave up by 1. And indeed, my vertical shift is up 1. So if I connect these points with a sinusoidal wave, I will have a maximum that reaches the midline, then its minimum, back up to the maximum, and this pattern repeats. I can check. Does my wave have an amplitude of 3? Yes. Does it have a period of 4 pi from maximum to maximum? Yes. Does it have a horizontal shift of pi to the right? This is a little challenging to read. Horizontal dilations are the most difficult to understand because this horizontal dilation is affected by both the right slide and the horizontal dilation factor. I know that my midline has gone up 1, and I must move the entire wave to the right by pi if the point that had no horizontal distance, the one that was the y-intercept, moved over by that amount.